Today's topic is biological filtration, still in the filtration stage of HWTS. The most widely known form of biological filtration is called slow sand filtration, and it has been used for centuries to purify drinking water. In the past few decades, slow sand filtration has been adapted for use at the household level, where it is most commonly known as biosand filtration. While slow sand filtration is superficially similar to rapid sand filtration, it's actually quite different. We saw in the membrane filtration lecture that sand filtration alone can remove large particles through size exclusion, but that pathogens and even relatively large protozoa are still smaller than the pore spaces and can pass through. Some pathogens will attach to larger particles which are removed, and some pathogens will adsorb onto the surfaces of the sand due to electrostatic effects, but rapid sand filtration has only a small impact on pathogen loads. Biological filtration includes these same size exclusion processes and electrostatic ones, but critically, it also includes biological activity. In biological filtration, a biofilm develops on the surface of the filtration sand. It's not a thick, green, slimy layer that you can see. It's a very thin, biologically active layer. And then organisms in this active layer, this biofilm, can actively consume pathogens that are present in the untreated water. And this gives a much greater pathogen reduction than filtration alone. Biological filtration is also much slower than rapid sand filtration, and there also tends to be a long residence time within a filter where some of the pathogens will die off naturally due to lack of food or oxygen, or the temperature is not convenient, because they're mostly adapted for living in the intestines rather than in a sand filter in someone's house. Let's look at some design parameters for conventional slow sand filtration. Slow sand filtration consists of two main elements. One is a bed of packed sand, and the other is the water column above it. And both of those tend to be around 1 meter in depth, where the water column might be from 60 to 120 centimeters, and the sand bed, again, from 80 to 120 centimeters, maybe as low as 50 centimeters. The type of sand that's used in the bed is important. It shouldn't be too big or too small. It should also be fairly uniform, and often people aim for an effective size of around 0.15 to 0.35 millimeters, where the effective size is the D10, or the size which 10% of the particles are smaller than. And a guideline for uniformity is that the uniformity coefficient should be around 2 or 3, where the uniformity coefficient is the ratio of the D90, the size of the 90th percentile particle, to the D10. Slow sand filtration is conventionally operated in a continuous flow mode from up to down, with filtration rates of around 10 to 30 centimeters per hour, occasionally up to 50 centimeters per hour. It's important that the biologically active layer, the biofilm, should never be allowed to dry out because it would die. So slow sand filters normally have some kind of flow control, a hydraulic control, so that the water outlet is higher than the level of the sand bed, and it can never run dry that way. Another thing about slow sand filtration is that when putting a new filter online, it takes some time for the biofilm to develop. About a month, usually. It's called a ripening period. And then the layer that forms is called the Schmutzdecke, or the dirty layer, even though that's actually where a lot of the important pathogen removal processes take place. Biosand filtration is basically slow sand filtration scaled down for use at the household level. There are many different designs of biosand filters available. This picture is one promoted by COST, the Center for Affordable Water and Sanitation Technology, and this is their version 10 biosand filter. In this version, it has the same elements as a conventional slow sand filtration, a water layer. Here it's 5 centimeters deep, which they say is optimal for allowing oxygen to diffuse through. And then a sand bed. Here it's 55 centimeters deep. And the sand that's used in a household biosand filter can be a little bit larger than in a conventional slow sand filter. COST recommends that the sand should pass through a 0.7 millimeter sieve. But one of the biggest differences is that the household biosand filter is operated intermittently with batches of 12 liters in this design, and also the pore volume in the sand layer has a volume of 12 liters. Now, this model also has a hydraulic control so that the outlet is here, which is at the 5 centimeters level, so the water will never run dry. And with a cross-sectional area of about 600 square centimeters and a design rate of 40 centimeters per hour, that translates to about 400 milliliters per minute, which can be treated, or 24 liters per hour. So that means one batch of 12 liters should take about half an hour to be completely treated. Biosand filters are conventionally available with a concrete housing, such as the one shown here. And in recent years, plastic housings have been developed that are much more lightweight and easy to transport. In both conventional slow sand filtration and biosand filtration, a new filter needs some time, about a month, to develop the Schmutzdecke, the biologically active layer. Now, like membrane filters or ceramic filters, a new filter has a pretty high flux rate, which slowly decreases over time as the filter media becomes fouled, as particles get trapped in pore spaces. In membranes or some ceramics, flux can be restored by backwashing, but that's not done in biosand filtration. What's done instead is in a conventional slow sand filter, the top layer is scraped off and stored for later use, usually about 1 to 3 centimeters. Because this includes a lot of the Schmutzdecke, then there's an additional ripening period that's needed of about 7 to 10 days. And in a typical slow sand filter, this type of cleaning is done every 20 to 60 days, depending on the water characteristics and the flow rates. For biosand filters, a slightly different approach is used, which COST calls swirl and dump. It's what it sounds like. A bunch of water is added to the inlet and then manually swirled around, breaking up any dirt that's in the first few centimeters of sand. And then that dirty water is dumped and removed. The process might be repeated if the sand's very dirty. Because much of the biological Schmutzdecke remains in the sand isn't removed, the ripening period is less, and COST recommends just a few days of ripening. The frequency of such cleaning at a household level really depends on the quality of the water and the amount of water that's treated. There are some good operating procedures which can help to get the best performance out of a biosand filter. One of these is to use a consistent water source. The Schmutzdecke is a collection of microbes, and they get habituated to a certain kind of water. So if the raw water is changing from surface water to groundwater or rainwater, these are very different, and the biofilm won't be happy with that. It's also good if the raw water is not very turbid, say less than 50 NTU, because those particles can clog the filter. It's important to use the filter each day, at least one time, and perhaps 3 or 4 times. When the filter is not used, the dissolved oxygen in the water can be consumed, and this can be bad for the microbes in the filter, including in the Schmutzdecke, which are important for good performance of the biosand filter. Similarly, it's important to make sure that the biological layer is always wet. The Schmutzdecke will die if it dries out. And many of the systems have a hydraulic control so that the outlet is above the sand layer, but still it's important to check for leaks and make sure that that sand is always wet. Likewise, it's important to check the flow rate. If the flow rate is too fast, treatment may not be effective. And if the flow rate is too slow, it might be time to do a cleaning. Finally, biosand filtration doesn't give any residual disinfectant, so it's important to collect the water safely in a safe storage container and manage it hygienically after treatment. So how well do biosand filters do at removing pathogens? Well, they work best for the larger pathogens, the helminths and protozoa, because they're easier to strain out physically or to absorb onto the sand layers. So typically you'll see more than 2 log removal of helminths and protozoa. And remember, LRVs in this table stand for log reduction values. Bacteria slip through a little bit more. You typically see 1 to 2 LRV in a biosand filter. And viruses are typically not terribly well removed, with maybe about 70% removal being typical, which is less than 1 LRV. Some physical and chemical components are also removed through biosand filters. Turbidity is nicely removed with about 90% removal, 85 to 95%. Iron is well removed because it oxidizes within the filter and precipitates out on the sand coatings. So you might see 90 to 95% removal there. A typical biosand filter will not remove arsenic, but there is an adapted version which includes an iron source, usually iron nails, which is much more effective at arsenic removal. But arsenic removal is complex, and competing ions such as phosphorus and silicon can very highly affect performance. Finally, the filters don't remove nitrate or nitrite, but they can actually increase nitrite by converting ammonia into the oxidized form nitrate. This can cause treated water to exceed health-based guideline values. So it's always a good idea to keep an eye on the nitrogen chemistry. Look for ammonia as well as nitrite in waters that have been treated with biosand filtration. Now let's give an example of a field application of biosand filters in Cambodia. One of the first organizations to work on biosand filters in Cambodia was Samaritan's Purse from Canada, an NGO, in partnership with 2 local NGOs, Hagar Cambodia and CGA. Together, these NGOs have implemented over 100,000 biosand filters since 1999, with a capacity of more than 25,000 per year. In 2007, an evaluation was made, which was published in 2010. This was sponsored by the World Bank's Water and Sanitation Program and was a very rigorous epidemiological study that looked at 105 intervention households from the 2 NGOs' working areas with 102 matched controls, so they could tell if any changes were due to the treatment and not just to changes over time. The evaluation found high use of the biosand filters. 88% of them were in use at the time of visit. And of the 12% that weren't in use, the most common reason was dissatisfaction with the taste or the odor or the color of the treated water. The filters had been in place for a median of 2 years, and in one case had been in use for 8 years. 2/3 of the survey respondents reported receiving some training from the NGO workers, and among those who did receive training, they were twice as likely to use the filters as those who didn't receive training. Now, according to the NGO programs, 100% of people were trained during distribution, so either there's been some turnover of people or people simply don't recall having received the training. One important finding was that the treated water was always stored at the household level. And you can see from this design that you need to collect the water in some kind of storage. However, about half of people were storing it in used open containers like this one. And about 80% of people were taking water from the container using a dipper or other instrument that could introduce contamination. The evaluation found that E. coli was reduced somewhat by the biosand filters. If we first think about high-risk waters, which are considered to be those having at least 100 CFU, E. coli per 100 mils, well, the raw water, 73% of samples were in this high-risk class, and only 13% of treated water was considered high risk, and that was a significant difference. However, only 4% of the treated water samples had no detectable E. coli and then would meet health-based targets. Storage introduced recontamination or allowed regrowth, and almost 1/3 of samples were in that high-risk category in the storage container. So on average, there was about 1 to 2 log reduction values, or about 95% E. coli removal, and this was highly variable. It's actually quite complicated to calculate log reduction values because of the large storage volume in the filter. So the sample you collect is not exactly the same water that you just poured into the filter. And again, stored water did increase E. coli levels by about 0.8 LRV. The filters did significantly reduce the turbidity of the raw water by about 80%. Well, let's consider then some of the advantages and challenges of biosand filtration. First, operation is quite simple. You pour water in and you get filtered water out. But it does need regular cleaning, this swirl and dump method, and the filter should be left to ripen after cleaning, so that can be a challenge. The filter in general doesn't change the taste or the odor of the water, but it does leave filtered water with a high risk of recontamination, especially when safe storage isn't applied. Users really appreciate the great reductions in turbidity, but you should not expect that the filter has much of an effect on chemicals, except perhaps iron. And in fact, nitrogen might be made worse. Ammonia could be converted to nitrite. Biosand filters can be manufactured on site, the concrete models at least, but then those concrete models are very heavy, more than 150 kilograms when they're full. So once they're put in place, it's very difficult to move them around. It's also difficult to transport them to the household level if they're collected at a central location. There is evidence that the filters are used for years consistently, but the same studies have shown that the effectiveness in removing pathogens is rather limited. This has been just a brief introduction to biosand filters, and I'd like to give you some places where you could find additional information. First, Manz water filters. David Manz was one of the pioneers in developing biosand filters in Canada, and the website has a lot of useful information. Cost, we've used some of their graphics on this lecture, and they have quite a number of documents, including training materials, construction manuals on their website. Samaritan's Purse, which supported the work in Cambodia as well as many other countries, has some nice documentation on their website, including a really nice animation of water passing through biosand filters. And then biosandfilter.org itself is another good repository of information. I'd like to point you also to two general portals about water, including household water treatment. This is sswm.info and ACVO, that both have good general information on biosand filters as well as other HWTS processes. So in summary, we've learned today about biosand filtration and how it's an adaptation of slow sand filtration for use at the household level. We've looked at some of the similarities and differences between biosand filtration and conventional slow sand filtration, and have gone over the operation and maintenance, including this important step of cleaning the filter when the flow gets too low and allowing some time for ripening to reestablish the efficiency of treatment. We've gone over some of the advantages and challenges for biosand filters, and one of the significant challenges is definitely only moderate pathogen removal, 1 or 2 log removal for bacteria, less than 1 log removal typically for viruses. So it's best to think of biosand filtration as a filtration technology, but not a disinfection one, and one that should always be followed with safe storage and ideally disinfection.